Hello. Can you hear me? Hello. Can you hear me? Okay, perfect. Great. So, any questions, queries? How's it going? Everything good? Last week for what? Lectures? Really? Oh, I guess. I mean, we did lose a couple of weeks in the start. Yeah, but I guess we can, I don't know, end the lectures this week maybe. Did you receive any end on this? Oh, okay. I didn't know that. So 17th, right? So which means next Monday. Okay. Cool. Did you receive any updates on the final exams? Because of course those can't be held now. None yet. Yeah, I don't know why. Anyway, okay. Let's talk about that at the end of the lecture maybe. If, I don't know, there's much to talk about that. Do you have any questions or should I just begin? Okay, perfect. So let's see. Let's just review what we did so far. So we did logic and proofs. Oops, let me fix my pen. Pen. Okay, this should work now. So we did logic and proofs. So we did chapter 1, logic and I don't like this color. Okay. So logic and proofs was chapter 1. Then we did functions and series. This is chapter 1. Chapter 2, function series. Cardinality, I think that was also chapter 2. Chapter 3 was complexity of algorithms, complexity and growth and blah blah. 4 was number theory. Right? And then I skipped, I believe, So what was chapter 5? Chapter 5 was about induction and recursion. Actually, we did do mathematical induction, but we didn't do it in much detail. And to me, induction is sort of related to chapter 4 and chapter 1. So we did mathematical induction, right? Mathematical induction. And then we did one topic from chapter 6 and one topic from chapter 8. So this was the pigeonhole principle, and this was the inclusion exclusion principle. Right, so we've not covered a lot of the material. I've skipped a lot of material in chapters 5, 6, 7. 7 I've excluded completely because I think that's part of your Intro to Stats course and Inferential Statistics course. So probability is something that I've not done with you, but discrete probability is also interesting. But yeah, chapter 6, chapter 5, 6 and 8, I've skipped a lot of stuff. You can check them out. It's got interesting material. Of course, we can't really do that. Even in a regular semester, we wouldn't have been able to cover most of that material, but you can still, you have the basic understanding of some of the topics of these chapters, and you should be able to, if you wish to look at other topics, then you can do that as well. Chapter 9 is something that I completely skipped again, just like chapter 7. And now I'm going to move on to graph theory. And of course, we can't do much in graph theory as well, since I guess we have these couple of lectures remaining. So I just want to introduce graph theory. So this is my last module, which is on graph theory. And I want to just give you an introduction, and hopefully you get a sense of the basic concepts in graph theory, and you can get a sense of the kind of problems there are in graph theory and how they're approached, and possible applications. Graph theory has got lots of applications, especially for those of you who are doing computer science. It's heavily applied in computer science. And so in networks and social networks and web graphs and lots of applications of graph theory. So, and there's lots of interesting problems related to graph theory. So from the lens of a mathematician, it's interesting if you can ask interesting mathematical questions about it, right? And so graph theory opens itself up to interesting mathematical questions, and you can pose some of that problem. I will introduce some of those problems, even if we don't necessarily get to discuss their possible solutions and how to approach them. I will still introduce them so you get a sense of what kind of issues you're looking at in graph theory, right? So let's start. Let's start with a graph, right? And so first, the best way to visualize, the best way to define a graph is to see a graph visually, right? So let's just see a graph. So a graph has basically two components. The first is it has some vertices. So it has some vertices and edges, right? These are the two components, constituents that make up a graph. So let's say I have a graph such as this, which has 3 vertices. So let's call this V1, V2, and V3, right? And so these points, these are called vertices. You can also call them nodes perhaps. And if there are any connections between any two of them, those are called edges, right? So edges, let's make possible edges between those. So let's connect V1 and V2, V2 and V3, V1 and V2, and so on. So these are called edges, right? E1, E2, and E3, right? Now, the first thing to notice is that we've given a visual picture of it, right? But we can also state it as, we can state this in a notation, in a mathematical notation, by saying if the set of vertices is v1, v2 and v3. Now that's clear, you don't need to state anything else for these vertices, but when you talk about the edges, if you just write e1, e2 and e3, that's incomplete, right? I don't really get this entire picture unless I know which this edge connects which of the two vertices, right? So a nicer way to represent this would be to say, so there's an edge that connects v1 and v2, there's an edge that connects v1 and v3, and there's an edge that connects v2 and v3, right? So now this gives you the entire information about your graph, right? So you don't need a visual picture for a graph. It's nice if you can draw it. And also something to note about the visual pictures is that I can draw this graph exactly the same graph in a different way, right? I could have drawn this like this: v1, v2, v3. This is v1, v2, v3, and then I can draw the edge e1, which is this, so e1, and then e3, which is v1 to v3, e3, and then there is another edge that connects v2 and v3, and I can draw it like this. And there's absolutely nothing that's stopping me from making this into a curved line, or making this into, putting these vertices in a straight line, or perhaps some other representation as well. So these are all equivalent representations. These are representing the same graph. There's nothing unique about a visual representation of a graph, yes? But once you describe it mathematically like this, now of course this is unique. There's no other possible way to describe this, right? And so this is a unique representation of the graph, right? Yeah. Okay, and so there's several things that you can play with. So one of the restrictions that I've put is, not that I've put that restriction, but there's nothing stopping us from making perhaps multiple connections between edges, right? So maybe I can say there's between v1 and v2 there's multiple edges, right? And I could have maybe a graph like this. Maybe you don't have any connection with this vertex, right? So this is another graph, right? And you can represent it by using, so this was graph 1, and graph 2 can be written as v equals to, now I can v1, v2, v3, v4. So the list is v1, v2, v3, v4. And the list of edges is, you can list all of these edges. There's two edges of the kind that connect v1 and v2. So v1, v2, there's an edge that connects, another edge that connects v1 and v2, and an edge that connects v2 and v3, and an edge that connects v1 and v3, right? So this is another mathematical representation of the other graph that we've drawn over here. Okay, so draw a line. Okay, so there's also nothing stopping me. So first, this kind of graph, which only has at most one edge connecting each of these edges, and there's also a possibility that you can connect. So let me draw one more graph before I start labeling them as such, right? And so let's draw another graph, which is like this. And of course I could put these edges anywhere. And so if there's a edge, it's also possible for you to connect an edge with itself, right? Connect a vertex with itself. So it's possible to draw an edge that starts from the same vertex and ends at the same vertex, right? So this is also an edge, but this edge is basically, if the vertex was v, then this is v comma v, right? And so the first kind of graph that we've drawn is called a simple graph, right? So this is called a simple graph, such that it only has at most one edge going from two different vertices, and the connection that it makes is from one edge, one vertex to another vertex. It never connects the same vertex with itself. So basically it doesn't contain any loops, so there's no loops here, right? This edge that I drew that connected a vertex with itself, that's called a loop. Okay, this graph on the other hand is called I believe a multigraph. Let me just check whether it's called a multigraph, in which you can have multiple edges between vertices, and the graph that allows you to draw loops, that's called a pseudo graph, right? So in a pseudo graph, multiple edges are also allowed, so you can have edges like this, so like this, and you can also have loops, right? So these were examples of, now all of these, by the way, were examples of a kind of graph that there's no direction in these edges, right? It's also possible to draw a graph in which the direction in which this edge is going, that's important, right? So for example, if I draw a network like this, perhaps a vertex, and if I draw a possible graph like this in which the direction in which the edge is going, so for example, I say this edge is going in this direction, and this edge is going in this direction, and there's also another graph that's going in this direction. This edges which have some direction, graphs in which edges have directions are called directed graphs, right? So up until this point, all of these graphs were undirected, right? So this was a simple undirected graph. This was a multigraph, which is also undirected, and this was a pseudo graph, which was also an undirected graph. And now again, in directed graphs, you can have different classification. So in a directed graph, you can have a simple directed graph, you can have a mixed graph, which basically means that you are allowed to have multiple edges and loops. So mixed directed graphs, and you can have also there's a mixed graph, right? Directed. So you can have let's call this a directed multigraph, in which you allow multiple edges, and then you can have a mixed graph in which everything is allowed. You can have directions, you can have multiple edges, you can have loops, every possibility is included in that. Okay? So that's the basic starting point of a graph, right? Now, there's lots of applications, and I suppose it's a good time to discuss the application. So, for example, you can use graphs to represent social networks, and this is not just online networks, this could also be just physical networks between people, right? And so the idea is, let's suppose we can have an acquaintance graph. For example, if we're talking about the students of IBA, then let's suppose I have lots of students going around in the IBA campus. Well, not anymore on campus, but So now the question is, these are all students, right? So this is student 1, student 2, student 3, and the acquaintance graph basically will tell me if one student is an acquaintance of another or not. So maybe there's these two students are acquaintances, these two students are acquaintances, this student and this student are not, and so maybe you can have some network like this, and you can imagine drawing all these edges, maybe some complicated network like this, right? And so which will basically tell you all of the possible social connections in students. Maybe this student doesn't have any acquaintance, doesn't talk to anyone, right? And so this graph will tell you everything you want to know about the social well, most of the connections of acquaintances that you would like to know about students at IB, right? So which student knows and interacts with which student, right? So that's one possible application of graphs, right? Where the vertices will be students, and you draw an edge UV exists if student U is an acquaintance of V. And you can also immediately classify this, right? This is not a there won't be multiple connections in it, because it makes no sense to have a connection. Like, I don't see why you would draw a multiple connection between two students, because if they're acquaintances, there's not much to know. Perhaps if you wanted to represent a degree of friendship, perhaps, then maybe you can draw stronger links between them. So maybe if they know each other, if they're just acquaintances, then you have one link connecting them. If they're if they've interacted more than 5 times, then you can draw another link between them, right? But if it's just an acquaintance graph, then it makes no sense to draw multiple connections. So this graph is just a simple, and of course there's also no sense of direction here, right? If student 1 is an acquaintance of student 2, then I don't see a need to draw any direction here, because it's a bidirectional relationship, right? So this is a simple undirected graph, right? On the other hand, let's say you were making a network graph, and at this point I'm talking about computer networks, right? So for example, let's take a simple example. Let's say I'm talking about the connections I have in my home. So let's say so let's represent this edge as the my ISP, and this is my internet router, and then it's connected to my phone. It's connected to my parents' phone, so phone number 2, phone number 3, and it's connected to my laptop, it's connected to a tablet, right? And so I can draw connections like this. So my ISP is connected to the router, and then my router connects. Did I just write a table? I meant a tablet. Okay. And so the network links are as follows, right? So like this, oops, Control C. So my router connects to my laptop, my router connects to phone number 2, and my router connects to phone 3. If I were using perhaps some kind of this represents all of the network connections in my home, right? If I was using some kind of perhaps a hotspot situation in which I was using my phone to connect to my laptop, then my phone's internet to connect, maybe then I can draw another link here, right? So if I was using my data connection to connect to the internet, then that would represent another link between the phone and the laptop, and perhaps a separate ISP. So another separate ISP would be directly connecting to my phone, and then my laptop was connecting to my phone, right? So these are all the possible links in my home network connection. And now in this one you can have multiple links as well. So maybe I'm connecting between my phone and my laptop using a Bluetooth connection. Maybe I'm connecting using the Wi-Fi. So it makes sense to make multiple connections here. And it's also possible, it's maybe not in this situation because we know they're mostly bidirectional, but if, for example, you were representing if you're only downloading or uploading. So if you're only downloading, then you would have a direction in this direction, right? So if all of these were only allowed to download material and not upload material, then from the ISPs, then it would be something like a directional graph, right? So you can only download. Right? That's simplifying matters a lot because you do need to send signals, but That's one way of connecting. Or maybe you could draw a network that represents landline network, right? So there could be a landline network which could basically represent, so there's a central I don't know what they're called, the operators, or I don't know, which connects all of the telephones in a particular region. So a central location to which all of the telephone lines are connected. So it has a connection here, it has a connection here, it has a connection here, here, and here, right? And so that's from one particular region. And then if you want to go to another particular region, so let's suppose there's another station here, and then that's connected to the different telephones over here. So let's say this is a connection, this is a connection, so on, right? And then these two regions are also connected with each other, right? So a possible graph like this. So of course there's lots of them, and there could be, millions and millions of nodes and connections between those nodes, right? Yes, server, yeah. What's your question about the server, Imad? Oh, Kiblathan, can we have multi-edges in the acquaintance graph? Okay, I think I've answered that. And Imad, I don't understand your question. I'll wait for that. And let's so that's also another possible graph that you can make, right? So networks can be really interestingly represented, or very easily represented, using graphs, right? That's an immediate application of graph, right? Okay, there you can also, the main body would be a server. Oh, in the landline network, maybe, I don't know. I don't think they're called servers. I don't know. It's age-old technology, landline networks. I don't know if anyone uses landlines anymore. I'm sure they do. PTCL still exists, so I'm guessing people still use landlines. You can think of the phone ISPs and IBA, so you can think of all the connections over there, right? So between different faculty members and so on and so forth. You can also draw a collaboration graph. So for example, in an academic setting, let's say faculty members are publishing research papers, right? So let's suppose let's say you have the maths department, and there's let's suppose different faculty members who've, now let's suppose I will draw let's suppose all of these represent faculty members in some department of a university, and if some people have published a paper together, then you can draw an edge between them, right? So perhaps if you have them in the applied math department, then there will be possibly many connections between people, and you can of course draw multiple edges as well, representing the published more than one paper together. So perhaps if these two professors have done a lot of work together, then you can represent this with a multiply edged graph, right? And so let's suppose this is one part of the network, and then you have let's say this was the maths department and this was the social sciences department, and I would imagine that there's lots of connections between this cluster in itself, let's suppose, right, like this, something like this, right, this, like this. But it would be very difficult, I would assume, to find a connection between vertices in this cluster to vertices in this cluster. I would imagine not a lot of social sciences professor would be publishing papers with mathematics professors, right? And so if they did, that would be really interesting, but usually it doesn't happen. So you can have clusters in a graph where these are not connected to each other, right? So you can almost see them as two different graphs, right? Okay, and so there's no, let's not get into that detail immediately. Okay, you can also, by the way, model the entire internet. So let's suppose I want to draw the web graph, right? Where I represent each website. So let's say one node, this node represents Facebook, and this node represents Google, and this node represents what else? Twitter and Microsoft. And let's say you have all of these websites, then you draw a connection between them if there's a link from a Google website that directs you to Facebook, right? So if you click a link on Google that takes you to Facebook, then there's an edge connecting Google and Facebook. If there's a link that connects you from Facebook to, let's suppose, Twitter, then there's a link between these two, right? So you can draw the entire internet, you can represent, and of course you can have multiple links, and it's going to be a very, very large, there's going to be millions, and I don't know how many, probably billions of websites now. And so there's going to be lots of connections in this graph, right? So you can map out the entire internet by just seeing what websites have links to what websites. And by the way, if it's a really popular website like Facebook or Google, you would imagine lots of other websites have a link to that website, right? So for example, if you want to draw, you can even give it a direction, right? And you would imagine there's lots of links going to Facebook, and Facebook would also be taking out lots of links as well, right? And so you can have links in the other direction as well. So maybe this link takes you to Facebook, but there's no link on Facebook that takes you to that website, right? And so maybe you have connections like this as well, right? So you can map out the entire internet using a graph, right? And you can imagine this to be a very complicated graph indeed, right? There's going to be lots of nodes, there's going to be a lot of connections, and actually I can't even, until I start traversing it, I don't think I will be able to recognize what sorts of, so let's say I want to find out what the internet looks like as a graph, then I need to start somewhere, right? And so if I need to start, let's say I start from Facebook and start making down all the connections there are to Facebook, that links that go out of Facebook, and then from those links I go out further and see what other links are there, and this way I can traverse and find out all the possible edges, right? Okay. What else? Citation graphs, and something that's important in computer science and actually programming is you can draw a module dependency graph. For example, if you're writing I'm not sure how frequently graphs like this might be made in a computer science setting. I don't have much experience with software development, but it's really possible to, if you're writing a complicated program, if you have a complicated program, then what you do is write your first thing that you do when you're writing a large software is to break it down into modules, right? And the idea behind modules is that basically one block or one piece of software, one piece of code should perform only one function, right? So if you want to write down perhaps let's say if I'm writing a software that compresses perhaps UML diagram, I'm not sure what that is. Let's see. Let's Google that. UML diagram. Right, yeah, something like that. Visually a system along with its main actors' roles. Yeah, it also looks like a graph, yeah. Right. And so the idea is basically you take it down. I'm not sure if you can have module dependency even if you don't have object-oriented programming, So the idea is, let's say you've written different modules, right? And so the idea is, let's suppose I was writing down a software, perhaps for my research, that was doing some sort of algorithm, right? So I was running some algorithm, I was trying to make an algorithm, and it had several components, right? So even let's suppose if you were writing just a simple sorting algorithm, we can break it down into different modules, right? So let's say I wrote different pieces of different files for different functions, right? And so these are different modules in my code. And so a module dependency graph would tell me which module depends on which one. So maybe if I have my main function, if this is my main file, then the main file will be calling the other files. But it's also possible that one of these files calls some of the others, right? So this would represent connections between different modules of a graph. And of course, there's no reason to draw it into squares. You can just simply represent each of the modules using a node, and you can immediately turn it into a graph, right? So if these are modules that are representing different, if these are nodes representing different modules, and the main module would be connected to most of them, and then maybe these other functions will be calling these sub-functions, something like this maybe, right? So I can have a code like this where this is my main file. So let's say this is my main file, and I want to keep the main file as clean as possible, so it only calls a bunch of other functions, let's say only 3 other files, and then these 3 files are depending on these other files. So if you don't have a dependency file, so sometimes when I'm installing a software on my program, so let's suppose if I'm installing a program that requires others, so that's something called dependencies on Linux, and that's also something that you might see in a Windows program where you're trying to install a piece of software but it won't work because you don't have another required software for it. So those are dependencies which you need to have if you want your software to work, right? Because that's code built upon other codes, right? And so you can draw a graph like this to represent your module dependencies, right? And you can of course have airline routes, so routes, so you can show transportation networks. So maybe if I'm connecting, let's suppose, different train stations together, so let's say I have this train station, all of these train stations, then I can draw a graph, maybe kind of a subway graph if you've seen. Then each node represents a station, each vertex represents a station, and each edge represents whether a train goes between 2 connections or not, right? So between 2 stations or not, so station 1, station 2, and so on and so forth. And of course you can draw a graph, such a graph for airline routes, or you can draw it for train networks, you can draw it for subway networks, and so on and so forth, right? In parallel computing, by the way, let's say you want to do parallel computing, right? Let's suppose you have a piece of code, let's suppose line 1, line 2, line 3, line 4, line 5, line 6, line 7, and if you want to take advantage of parallel computing, what you want to do is we want to see which of these statements can you run independently, right? So let's say, for example, the first statement says a equals to 5, b equals to 4, and then the next statement says c equals to 5 plus 4. If this was statement 1, statement 2, and statement 3, I can run statement 1 and statement 2 independently, right? There's no need for me to wait for statement 1 to finish execution before I start executing statement 2, because statement 1 stores a variable, statement 2 stores a different variable. But for statement 3, I need to wait until statement 1 has finished its execution. So I can maybe draw a directed graph like this, that until statement 2 finishes, I can't move on to statement 3, right? But once statement 3 has finished, then maybe let's say I have another statement that says statement 4 says d equals to c plus 2 and statement 5 is d equals to c minus 2, then of course there's no reason, sorry, not d, this should be something else, so let's say e. If I want to start executing statement 4 and statement 5, there's no reason for me to finish executing statement 4 before I start statement 5. So if I have statement 4 and statement 5, there's no link between statement 4 and statement 5, so I can wait. I don't need to wait, and I can run them concurrently, right? So such kind of graph will be useful in telling you where can you take advantage of parallel processing, right? So at this stage you can do parallel processing, because you can give statement 1 to one processor and statement 2 to another processor, and they can both execute them and store the result. But statement 3 you'll have to do, at this point you'll have to do serial computing, because you have to wait for statement 3 to finish executing before you can again at this stage start a parallel processing, right? Because then statement 4 and statement 5 do not depend on this statement, and you can just give this to one processor and statement 5 to another processor and make use of parallel computing, right? Okay. And so that's various applications, and of course there's lots and lots of other applications, biological networks and I don't know, semantic networks, lots of other applications that you can make for graph theory, right? Okay, so that's a overview of the kind of application that you can have. It's very versatile. You can represent lots of things, and you can have a directed graph or a multi-graph or a mixed graph depending on the context that you're dealing with, depending on your application, depending on what you need to represent. You can have different kinds of graphs. Okay, let's move on. Let's move on to section 2. What can we do with these? What kinds of different questions can be asked, right? So let's go over a bit of terminology. So the first terminology is we define the idea of adjacent vertices, and the idea is that if there exists an edge EUV, so EUV that connects vertices U and V, then U and V are called adjacent vertices. And before I move on, I want to actually talk to you about something called the adjacency matrix. This is an interesting idea using matrices, and something that you might see in linear algebra when you take it, is that if there's a graph, then you can draw an adjacency matrices that looks like this. Let's first draw a table, okay? And on this hand, I will list down all the vertices. So let's say V1, V2, V3, V4, and V1, V2, V3, V4. And so let's say I have a graph like this. Let's say V1, V2, V3, V4. And let's suppose so this is V1, V2, V3, V4. And let's suppose there's a connection here, there's a connection here, there's a connection here, and perhaps there's a feedback loop over here as well, right? And so now if I want to represent all of these edges in a matrix, I can do it as follows. I will fill this table up with a 1. So the only thing that you're going to put is a 1 or a 0, right? You will put a 1 if there's an edge between V1 and V2, whichever. So when I start filling in this table, I will ask if there's an edge that connects V1 and V1. And so V1 isn't connected with a feedback loop, so I'll put a 0 here, right? Then I'll ask if there's an edge that connects V1 and V2. Well, yes, there is an edge that connects V1 and V2, so I put a 1 here, right? And so you can start filling out this table So this is v1 and v3, there's no link. v1 and v4, there's still no link. v2 and v1, of course, is going to be a link. v2 with v2, there's another link because this contains a loop. v2 and v3 have a link. v3 and v4 do not have a link. And v3 and v2, of course, this is going to be a symmetric graph, because if there's a link between v2 and v3, then there's a link between v3 and v2. And so there's no link over here, v3 and v1. There is a link over here between v3 and v2. So it's going to be a symmetric graph like this. And v3 and v3 does not have a link. v4 and v4 do not have a link. v3 and v4 also do not have a link, right? And v4 and v2 do have a link, right? And oops, this was wrong. Okay. And so this, now if you convert this into a matrix, then it looks like 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0. What you have is a nice little matrix that we call the adjacency matrix. And it's a nice little matrix because it's made up of zeros and ones, and it's a symmetric matrix as well, because if you take the transpose of this matrix, you get the same matrix, right? So it's a nice little application of linear algebra and graph theory that you find if you convert a graph into an adjacency matrix. Okay, v2 and v4 have yeah, sorry about that, Imad, I fixed my mistake. Okay, so that's the idea of adjacent vertices. The next idea is about the neighborhood, right? So the neighborhood basically, so n of v is the neighborhood of v, which is a set of all vertices adjacent to v. So for example, in this graph that I had drawn, if I want to label, let's say, n of v4, if I want to list down this set, then I have to list down all of the vertices that are adjacent to v4. And the adjacent vertices are, of course, where there exists a link. So v4 only has a link to v2, so the neighborhood of v4 is just v2. The neighborhood of v2, on the other hand, contains v1, v3, v4, and of course v2 itself as well, because it contains an edge from itself, right? So that's the neighborhood. And so a neighborhood can be of a vertex, but the neighborhood, you can also find the neighborhood A is the neighborhood of a subset of graph G. So let's suppose this graph was G and I take A as a subset. So let's say I take A contains v1 and v3 and v4. Then the neighborhood of A will contain the union of all of the vertices vi, such that vi is in A, right? Which means I want the neighborhood of v1 union neighborhood of v3 union neighborhood of v4. And so if I list down all of the neighborhoods, neighborhood of v1 is v2, neighborhood of v3 is also v2, and neighborhood of v4 is also. So this is not a very interesting example. And so this set was just v2, this set was also v2, and this set was also v2. And if I take a union of all of these sets, then I get just v2. So that's the neighborhood of this example that I've just given, right? So let's so this is related to the particular example that we were doing so far. Okay, so this is related to this example that we were doing. So let's perhaps maybe copy this and paste it here so that you know which graph we're talking about. Okay, so that's the neighborhood of vertices and the neighborhood of graphs. Okay, the next thing that we define is called the degree. define the degree of a vertex. So the degree of a vertex, the degree of a vertex is the number of vertices, number of edges incident on that vertex, which means it's basically saying how many edges are connected to that vertex, right? So for example, if we take this, by the way, so if we take this this example, then the degree of, in this example, the degree, so the degree of V1 is simply 1 because there's only one edge connecting it. But if you think about the degree of V2, then the degree of V2 actually is the notation, the correct notation is actually DEG. So just so DEG. So if we talk about the degree of V2, then it one edge, two edges, three edges. So three edges plus there's also a feedback loop, and this edge connects twice. So it also starts from V2 and also ends at V2. So I add it twice in the degree. So this is, so the degree of V2 is 5 because there's three edges that are going out of V2 and also one edge that goes out to V2 and comes back to V2. So basically a feedback loop or a loop adds 2 to the total degree of your vertex. So that's how you define the degree of a vertex, right? Okay. Any questions, anything? I think this is all simple. This is just notation and basic notation and terminology that we're going through so that we can talk about other interesting things. Okay, so one thing, so there's an, if a vertex, if the degree of vertex V is 0, then V is isolated. So it's called an isolated vertex if its degree is 0. That means that there's no edges connecting V to any other edge, right? And if the degree of V is exactly equals to 1, that is, there's only one edge connecting V, then it's called, then V is pendant. Fine. P-E-N-T-A-N-T. So that's called a pendant vertex if there's only one edge connecting them, right? Okay. And so at this point we can study the first theorem, and it's called the handshaking theorem, right? So the at this point we're starting, once we've had the notation, now we can turn ourselves into mathematicians and ask mathematical questions about the graphs. And so the handshaking theorem tells us something about the number of the total degree in a graph, right? So this is the theorem. So the theorem is let G VE be an undirected graph. So I had not brought out this notation so far. This notation basically is saying that this graph G is made up of a set of vertices V and a set of vertices E. So over here, when I first started defining a graph, then I can say that a graph is basically graph is a graph G which contains V and E, where V is the set of edges. So this is basically representing GV E, right? So these two combined together gives you a graph mathematically, right? So let GV be an undirected graph with M edges, with M edges, then the sum of the degree, the sum of all the vertices in V and their degrees, degree of small v, so this is small v in the set of vertices. If you take some vertex, and if you take all of the vertex and if you sum up their degrees, then this is going to be equals to, can you guess what this is going to be? This is going to be 2 times m. Right? And this holds for multiple edges and loops as well. Multiple edges and loops. Okay. Can you prove this theorem? Can you think of an argument that would prove this theorem? What does this theorem mean basically? This theorem means, let's suppose there's some, so let's say I had this, actually let's just bring out this graph that we had before, and let's say we're connecting these, let's see if this theorem applies here or not. So firstly, I want m edges, right? So I want to check the number of edges. So this is 1 edge, 2 edge, 3 edge, and 4 edge. So m is equals to 4, which means 2m should be equals to 8. And now let's start and count. So let's say I want to count the degree of v1 plus degree of v2 plus degree of v3 plus degree of v4. So this is the left hand side of the equation and this is the right hand side of the equation. And so if I do that, now the degree of v1 is of course 1 because there's only, oops, I don't want this, degree of v1 is just 1 because there's only one edge connecting v1, degree of v3 is 1, degree of v4 is 1, and degree of v2, we've already seen that it's 1, 2, 3, and there's one edge starting and ending at v2, so this is 5, right? And so the total is of course 8. And so this theorem is actually trivial if you think about it, because each edge contributes 1 to one of the once to one of the degrees, right? And twice if it's a loop. So the total number of, if you just add up all the degrees, it's going to be twice the total number of, because an edge starts at a vertex and ends at a vertex. So it's going to contribute 1 to the degree of this one and 1 to the degree of it. So one edge will contribute twice to the total degree of your graph, right? And so that's why this theorem holds. I don't think you need to prove this. This is obvious enough, right? And let's say we have another theorem, and at this point I think I'm going to end it. Let's just talk about one more theorem, which says an undirected graph, an undirected graph has an even number of vertices with odd degree, right? This is saying that if you have a graph, then some of its vertices will have an even number of even degree, and some of them will have an odd degree, right? So for example, in this example, you had v1 had an odd degree because its degree was 1, v2 had an odd degree because its degree was 5. Actually all of them are odd vertices, right? Odd degree vertices, because their degrees are odd numbers, right? And so an odd degree basically, so an odd degree vertex is a vertex with an odd number degree, right? So the degree of, basically the degree of v is sum 2n plus 1. That's how you represent a odd number, right? And so the idea is simple. The idea is that if you have, let's suppose in a graph you have vertices v, right? And so v1, v2, v3, dot dot dot, and I can partition them into ve, which contains all of the vi's, v's of even degree, and vo, which contains all of the vertices of odd degree. And the theorem is telling me that there are going to be an even number of such vertices. which you can see immediately in our example, because there were four vertices of odd degree, and 4 is an even number, right? And this is very obvious if you convert it into this and use the handshaking theorem. So the handshaking theorem was telling me 2m is equals to the sum of all of the degrees of vi, right? And I can, so v belongs to v, I can break this summation into two parts. Let's say I'm taking first the sum of all the even degree of vi, and plus summation all of the odd degree vertices, right? And this is equals to 2m, which means the left hand side is an even number. This is even, which tells me, and this I already know, all of these are even numbers, and when you add even numbers together you get an even number, which tells me that the total sum should be even. So the sum of these odd numbers is even, and the sum of some odd numbers can only be even if there are an even number of them, right? So if I have an odd number plus an odd number plus another odd number, so if there's an odd number of odd numbers, then I'm going to get an odd number. So there must be an even number of odd degree vertices. Does that make sense? Is that argument clear? Okay. I'm going to stop at this point because we've already taken an hour to discuss the basics of this graph theory, and hopefully you have some idea. I don't expect that I'll be able to do much with graphs, but let's see, I can maybe give you an idea of some of the problems associated in graph theory. Okay. Nothing else? Let's talk about ending this lecture. Okay. So it's, of course, we are at the end of the semester, and I think I'm satisfied with the material that we've covered so far. Of course, this is not a regular semester and I can't be too critical of what we've covered, but I think we've covered a decent amount of material in our time. And what else? About the exams, I don't know. There's, I don't know. Do you have any suggestions for what do you want to do for a final? Which I'm sure none of you wants to write another report for your finals as well. What do you think? Do you have any suggestions for the final? Should I give you a take-home assignment? How about I increase the weightage of your midterm report and make it part of the final? Because I'm assuming you're already doing lots of work for your midterm report, so might as well consider that as an exam. That's one possibility. An assignment is a possibility. If you want the midterm, I see some of you are quite excited about that idea. If you want that to be true, then you'll of course थोड़ी ज़्यादा मेहनत करना midterm report पे, because then it would be a final report and carry more weightage. That's how you will be judged. I don't know, any other suggestions? I guess those are the only two possibilities. I could do a Viva if you want, but given the response that I had for the Viva for the midterm, I don't think a lot of you will be interested in no Viva. Everything but an exam would be best case. Yeah, I don't think so. Okay. It's really not really scary. I would have taken a very easy Viva, but you guys are too afraid. That's okay, that makes sense. Scared you too much during the semester. Okay, if you have any other suggestions, just send me an email or put it on Piazza, but if you don't, then I'll think of something and decide between an assignment or increasing the weightage of your report. Would you be open to doing another report? Or maybe, how about this? Okay, let's say I take your first report as a midterm and I suggest to use some extension of that report to turn it into a final report. So you use the same material what you've learned and you do an extension of that report. So you do a second report which is basically a revised version of that report and submit it as a final. How about that? Does that seem reasonable? Yeah, basically you'll be submitting 2 reports, but you won't be doing okay, a take-home assignment is a much wiser choice if all the chapters are included. Yeah, I guess you can do a take-home assignment as well, maybe. But for a take-home assignment, I can't do much of a collaborative kind of. I can't restrict you from doing collaboration, and that defeats the point of the learning process for me. It'd be less time consuming if you already did one report. Yeah, that was what I was thinking, because you've already done something related to that topic, so it wouldn't take you that much time. You will just have to maybe revise the report in some way. Okay, maybe I'll just give you an option and see which one you go for. It might be up to you. So for those of you who would want to do an extension of your report, can go for that option, and for those who want to do an assignment, simply can do that. Okay, fine. Noted. Let me know if you have any other suggestions. All right. Nothing else. End this session. Have a good day. I hope you're all doing well. Take care of yourselves. And goodbye.